Okay, so this is a quick first poll question, and I'm asking about a piecewise function, and I just want to know the domain. So the domain is the x value. I want to know, is there an x value for which my function is not defined? Do we know? Is there an x value for where I won't have a y? 0. 0. So if I draw a number line, okay, cool. So if I draw a number line here, oh, that's not the right class. Okay. I'm going to draw it where we are on section 3. So I'm going to draw a number line to like describe which x values are actually part of my domain. Wait, here. So we're at the, you don't have to be on this page, but I'm drawing it that way it's part of your notes because I don't have anywhere else to draw it on my computer. Okay, so let me draw a number line that's going to stand for my x values. So the first point where I'm changing from one function to another, I don't know why this doesn't work. There. So I'm going from one function to another. The first one is, let's see, my y value is 1 if x is less than 0. So this is where 0 is located on my number line, and I know I will have x values as long as they're less than 0. My next jump is between 0 and 5. My next jump is between 0 and 5. So this is where 5 is, and once again I have 0. So it will be x squared if I'm between, but notice it's only a greater than or less than. It's not or equal to. Cool, okay. Are we confused what I'm doing? I'm just showing you, okay, where is x defined? So I'm drawing a hole if it's not or equal to. I draw a filled circle if it's an or equal to with a line under it. And lastly, I have if x is greater than or equal to 5. So I have, right here is my 5, and I have greater than or equal to. So if I'm asking, will I have a y value when x is 5? Yeah. Will I have a y value when x is 0? No, I won't, because there's no filled circle. What the heck? So literally, it's going to be any number except 0. So to write that in interval notation, I come over here. Let me pause before I write it. Do we understand why why the domain doesn't include x equals 0? The reason is because there's no y value associated with that number. If I'm looking at my graph, like blah, 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 what's happening, and then there's literally going to be a circle, an open circle. It's going to be a hole at x equals 0. There's no y value associated with it. Otherwise, I'll have a y value for any other x. Any other x I plug it in, I will get a y, right? I put in an x, spits out a y, depending on which function I'm dealing with. So, to write it, you go negative infinity to 0, comma, parenthesis union 0 to infinity. That's kind of hard to see. I'm going to write it on the calculator for you. Set up my, what? I threw my pen down and now, whatever. This pen is janky. Okay, so let me go to, oh, we're done. Nope, here. Okay, so I want to insert negative infinity to 0, comma, 0 to infinity. So how do I do it? You put parenthesis. Do you guys know where the parenthesis button is? Yeah, okay. And then I have to go do infinity, so I click on the pi button, click on infinity, except remember it's going to be negative infinity, so I put a negative sign in front of it. And then there's the comma. Comma is the very left button, very bottom left button. And then I want to go to 0, parenthesis. And there is a union button. Trying to remember where it is. Honestly, if you just put the U, literally the U, that's fine. Because I know you mean union, parentheses, 0, comma, infinity. So once again, you go over to pi, click on infinity, and there we go. That is the domain. Cool. Our next question. There's a reason why I'm like asking you these, because it deals with continuity. I have a y value at 5. The third function of my piecewise, I have a y value. Because it's or equal to. 5 is greater than or equal to 5. X is greater than or equal to 5.
Okay. Did you send it?
No, I did not send it yet. Alright, now I want you to find the domain of x plus 1 and x squared minus 1 over x squared minus 1. Ask the person next to you. Explain it to each other. My hint to you, denominator cannot equal 0. Ooh, so I got cut out the x values where the denominator is 0. So hopefully you know this because it was on your quizzy quiz, which will be, yeah, which you'll get back Monday. The people that were gone are taking it today and tomorrow. Waiting on 5 more people. This is the last quick poll question, and then we're gonna go on with the lesson. So the first question was like mostly review of like, okay, well, domain, all it has to do is have a y value. If it doesn't have a y, it's not defined, won't be in my domain. This question particularly is going to inform the next 10-15 minutes. Because although there's going to be 2 places where it's not defined, there's 2 different types of discontinuities associated with this equation. So, oh, okay, cool. So we're all submitted. So let's see what we got. All right, so let's see. Nice, this is correct. Okay, so we missed the negative one, which is okay. What's wrong with this one? Did you just like put a space? Oh, this should be a negative right here. Do you see where I'm? Oh, yeah. Let's see, this one is correct, this is correct. You just click on the U? You like hold it down or capital? No, we don't know. Okay, so pretty much get it. That's rad. Alright, so let's go over it. I'm gonna end the poll. Okay. So leave your hats on there. I'll take you out at the end, but if I want to like do another quick question, this allows me it. Okay, so I want to know what is the domain. So the top, x plus 1, is a polynomial. The bottom is x squared minus 1. That is also a polynomial. When you have a ratio of polynomials, it's called a rational function. It literally has the word ratio in it. So, okay, I know the domain for the top, if it was just alone, would be all real numbers. I know the domain for the bottom. If it was alone, if it was just x squared minus 1, it would be all real numbers. The issue is x squared minus 1 touches, like has a point where y is 0. So there'll be a number, well in our case 2 numbers, when I plug an x, there'll be 2 x values. When I plug it in, the bottom of my fraction goes to 0. That's not okay because it would be undefined. That would mean my y is undefined. So I know my denominator can't equal 0, so I'm going to find out where x squared minus 1 equals 0. So if I factor it out, this is a difference of squares. I see that when x equals 1 and when it equals negative 1, that's where the bottom would go to 0. So I don't want x equal 1 or negative 1. If I would plug those in, the bottom of my fraction would go to 0. So to write it, it's just like you're just cutting out those 2 pieces and taping everything back together. Try to think of like a good example of this. I don't know, because I don't really like cut things out a lot. Oh, I know. Good example. I made banana bread last night, and there was a little like mushy spot on my banana, so I just cut out that part of the banana and I used the rest. Here, I want to use all of my x values, just not that one. So I cut out the 1 and I cut out the negative 1, and then I use the rest of the banana, use the rest of the x values. No, this is a true story. I made banana bread. It was great. Yeah.
Why wouldn't you? Could you also just like add 1 to the 0 side and then find the square root of it?
Yeah.
Okay.
So you add 1, and you, x squared is 1 plus or minus square root of 1, so plus or minus 1. But I want you to get in the habit of factoring, because I'm not always going to give you a nice number like that. So if those are the only 2 numbers I want to cut out, I'll go negative infinity to negative 1, union negative 1 to 1, because I need to include the numbers between them, because it's the only 2 x's I want to cut out. I don't want to cut out 0. I don't want to cut out negative 0.5 or positive 0.5. Like I want all the numbers, just those 2 in particular, and then union 1 to infinity. All right, how do we feel about this problem? Are we okay with interval notation? Maybe yes.
The only thing is, what would it be though? Because if it's like so removable,
So that's what I'm about to like. That's why I picked this problem in particular, because you're like, wait, right? So Bradley's saying, wait, if I rewrote y in terms of its fully factored form, so x squared plus 1 on top, and then I have x plus 1 on bottom and x minus 1. Did I say it? Squared? Whatever. So if you have a factor that cancels out because it's on top and bottom, it's removable, and that's what we're going to go deeper into today. So it's removable, meaning the graph would just have a hole there and it would just keep going on. But it's still not defined. Notice I have a hole, it's still not defined. So I'm looking for domain. I just look at the bottom and say, where would it equal 0? But I'm asking for discontinuities. Well, at x equals negative 1, I would have a hole. But since if I would simplify this out into 1 over x minus 1, as long as x doesn't equal negative 1, oops. Oh my god, well, okay. I don't know, oh my god. So more or less what I'm doing here is I'm saying, hey, graph 1 over x minus 1, but I have to make sure I like draw my hole, the factor that canceled out. So when I graph 1 over x minus 1, whenever I reach the value of x equals negative 1, I just put a little hole. So this would look something like, let's see, so it looks something like this. That's what this function would look like. And hold on, so x equals negative 1, I forgot to draw my hole. So it looks something like that. Because the factor that cancels out is just a little hole on your graph. And then if I'm left with something that's still on the bottom, that's where my vertical discontinuity occurs. That's where my vertical asymptote occurs. Okay, this is literally what we're going to go into in more depth for the next 10-15 minutes. But in a more organized and better organized manner, because it's on your notes. Okay, different types of discontinuities. We talked about these a bunch of times. So now let's actually go over continuity test. We started talking about this yesterday. Let's dig in with a fresh brain. Continuity test. How do you know if something's continuous? It has 3 steps. First, The function value has to be defined. You have to have a y value at the x you're interested in. So if I'm asking you, is my graph continuous at x equals 1? All right, so I'm looking at 1. Is it continuous? It literally has to have a y value. If it's undefined, it will not be continuous. And like, that makes sense because remember, continuous is you're drawing your pencil and you don't want to pick it up. If you're literally undefined, you have to pick up your pencil and then restart somewhere else and start drawing. Cool. Okay. So f of x is defined as c. So you have to have a y value. F of x approaches the same value from either side. That means the limit has to exist. As I'm coming from both sides, I have to be coming toward the same number. So I have to have a limit, right? Imagine if I covered up the y value and I'm asking you to predict what will the y value be? And you're like, aha, I can tell because I'm looking at the data. It's approaching the same number. It has to exist. It can't be approaching two different numbers. It has to approach the same number. And then, literally, the function value has to be the same as the limit. So the number I'm approaching has to be the same value as what the y is actually. So if I have a graph that looks like this is not continuous. It passes the first test. Notice it has a y value, the filled dot. It has a limit, because if you're looking at the squiggly, you're approaching the same y. But this would be the case where the function value is not the same as the limit. Tricky trick. Okay, so example 1, determine whether each function is continuous at the given x value. Justify using continuity test on the test, which is the 26th. No, wait, I'm sorry, I'm looking at the wrong class. Which is the 20th, which is a week from today? Yesterday? I don't know, what day is it? A week from yesterday. So the 20th is your test over the first 4 sections of chapter 1. On your test, you have to use the continuity test, and I must see all 3 steps. If I don't see all 3 steps, you won't get all your points. There's literally partial credit with doing all 3 steps. Okay, I'm just being super extra about this because people didn't do it last year and they fought me on it, and I was like, dude, you knew, I told you. I'm telling you right now, you have to do all 3 steps. Okay, you won't forget. Example 1, determine whether blah, blah, blah. Okay, so I have this function, and I need to justify using continuity test. I have to run it through all 3 steps. If it's discontinuous, we have to identify, what is it? Is it a infinite discontinuity where I'm going toward infinity? Is it a jump discontinuity where I'm going, and then, whoop, I'm jumping up and I have a new function, so it's not the same function as I'm going through? Or is it removal where I'm going along, just have a circle and then keep going? So I have a function x squared plus x plus 1 at x equals 1. So the first thing I do, find the function value. Because remember, the first step, does it have a y? Then step 2, graph it and see if you're approaching the same y value. Does it have a limit? And then the third test is, are they the same? Is your y value the same as your limit? That's literally written out explicitly for you, the first example. First step, find f of 1. Go ahead and let's plug it in. So f of 1, plug it into the equation here. Wow, works like a dream now. Okay, f of 1 is 1 squared plus 1 plus 1. That's just 1 plus 1 plus 1, which is 3. It has a y value. All right, so we're checking if our y exists. It does. Okay, yes?
How would it not have a y value?
If it literally, just like the example we did before. What if I was saying, hey, this function at x equals 1? You'd plug it in and you're like, no, it's undefined. It doesn't have a y. Yeah. Or if I had y equals square root of x and I give you x equals -2. It doesn't exist. Yeah. Cool. Okay. Exists. Graph it on a calculator. Analyze the portion of the graph from the left and right of x equals 1 to see if they're approaching the same value. So you already have your calculator out. Wonderful. Oh no, is it stop recording? Please record. Oh no. Okay, cool. Sometimes it just randomly stops recording and it makes me so mad. All right, let's graph this function. Oops. document. Okay. So I want to graph it. Go to graph. Come on. I'm pushing it. So x squared plus x plus 1. Okay, and I want to zoom in around x equals 1. So I'm going to zoom in around x equals 1. Huh? Yeah, menu. Yeah, menu, window, zoom, and oops, no, menu, windows. Come on, I'm clicking. Stupid thing. Go back to standard. You could also trace. Do we see what it looks like it's getting close to? It looks like it's getting close to 3. So I am tracing, let's see, where x equals 1. It's getting closer and closer to 3. What? Menu, trace? Yeah. So if you look, like, it's looking like it's approaching 3. Cool. So it looks like we're approaching the same number. It looks like we're approaching 3. All right, so I would say the limit as x approaches 1 of x squared plus x plus 1 is equal to 3. So I'm doing limit. You're being a fortune teller, right? You're predicting what the y would be without actually seeing what the y is. So the limit as x is getting closer to 3. So as we're getting closer to our x value of 1, as I pick x values that are closer to 1, my y values are getting closer to 3. Okay, check. So guess what? Our limit exists. We're approaching the same number from both sides. And then the third part of our continuity test is, are they the same? Is my function value the same as my limit? Are they? Yeah, 3 is equal to 3. So this means it's continuous. It means it's continuous. Is this a surprise? No, because this is a polynomial. What's the domain of a polynomial? All real numbers. That means it's continuous. Your points of discontinuity are always going to be at the places that you cut out at your unions.
On our test is the answer. Do you want us to write yes or continuous?
Let's see. So determine whether each function is continuous. Yes. Continuous. It was just working fine. I don't know why it's not. It's continuous. F of 1 is equal to the limit as x approaches 1 of f of x. Right? 3 is equal to 3. That proves it. So are the results the same? Yes. Continuous. Function f of 1 equals limit of x as x approaches 1. So the next example, I don't think I spell it out as... No, I don't. I don't give you the steps. I'm trying to do gradual release, meaning hey, I'm walking you through it. That when you go on your homework, you're like, wait, how did I do this? No, I literally wrote it on your notes for you. But the next example is the same thing. But instead of saying f of 1, example B is oh, hey, at x equals 2. So everywhere you see f of 1, you put f of 2. Instead of saying f of x equals x squared plus x plus 1, our new function is x plus 1 over x minus 2. So we're going through the continuity test, all 3 steps. At the end, we say if it's continuous, good. If it's not continuous, we got to say, is it an infinite discontinuity, a jump, or a hole, which is removable. So step 1, we have to find the y value. Yes?
If there's no y value, you can still go on with the step.
I mean, we're going to, but... Because we need to tell what type of discontinuity it is. Because if we don't have a y value, okay, if it's an infinite discontinuity, the function's undefined there. If it's a jump, I mean, maybe the function's undefined there, and if it's a removal, it's undefined. So like, we gotta process elimination. We gotta figure out like which discontinuity it is. So by having it undefined, we know it's not gonna be continuous. We just have to figure out which one it is. Yeah, especially because the directions say use the continuity test. I want to see all 3 steps because there's points associated with all 3. If you don't show one of the steps, you don't get the points for that step. So we'll get there when we get there. You know what I mean? Like this would be on the no calculator portion. Oh, you're right. This would be on the calculator portion. Well, you write what the limit is, and you say, oh, if the limit's not approaching the same number, you say from left it's this number, from right it's this number. Like writing something. Yeah. So I'll show you on this one in particular. Okay, first step, find f of 2. What's wrong? Guys. Children. Okay, plug in 2. So I have 2 plus 1 over 2 minus 2. So that's going to be 3 over 0. That is undefined. So maybe automatically, do we know what type of discontinuity this is going to be? Infinite. Now we just have to like prove it. So when I take the limit as x approaches 2 of my function, oops, I want this side. So x plus 1 divided by x minus 2. I see I'm not approaching the same number, right? So the limit is not going to exist because from the left we're going to negative infinity, and from the right we're going to positive infinity. So although I used my calculator, I showed my process. I showed my train of thought. I looked at calculator, I see going down as I come from the left, going up as I approach from the right. And that means it doesn't exist. And then the third step, so D&E means does not exist, just like Lindsay Lohan, yep.
So would you not even write as x approaches?
Oh, I forgot. Yep. My bad. Thank you.
How did you know before you drafted that it was
Infinite?
yeah.
Because I have this on bottom. Like 1 over x is a hyperbola. Because hyperbole is English, so it's a hyperbola. So it looks like a... Yeah. So 1 over x. So anytime you have something over x. Yeah. And the cool thing is we're going to run into some graphs that are like really like wavy, whatever, but then the ends are like swooping off to infinities or whatever. Okay, and then the third step is this continuous? That was like one person. We should have a choir of 16 people singing. No, it's not. It's not continuous. Okay, so I say no, not continuous. All right, you literally see from your graph what type of discontinuity? Infinite discontinuity. Okay, wonderful. Wonderful. All right, so if you immediately knew what the answer would be, glory, because then there's like 3 free points. Like you should know every step would be correct. Trying to give you as many like partial credit points as possible, but that means you have to show all your steps. Okay. I think my goal is to say show your work 50 times every class period. That way I don't have to write it 50 times on your homework. All right, let's go to the next one, which is part C.
Wait, why is the left negative?
So as I come from the left, ready? As I come from the left, it's going down, and the going down is negative. So it's going down to infinity. Yeah, okay. So as I'm coming from the left with my x's, right? So here's x, it's 1, blah, blah. As I pick x's that are closer and closer to 1, what's happening to my y?
It's going down.
It's going down. So as I'm approaching x from the left side, y is going to negative infinity.
Oh, I thought. Okay.
So the limit is telling you, so the limit as x approaches 1, I'm literally wanting the y value as my x's get closer to 1. Okay, so first, First I want to find the y value. Does it exist? Okay, so I have to find f of negative 3. So I plug it in. I have negative 3 squared minus 9 over negative 3 plus 3. Weird, what happens? I get 0 over 0. So it's not just undefined. It's not something over 0. It's literally 0 over 0. That's really wavy. That's crazy. Yes? It's exactly what we're going to do. Yeah. Wonderful. Exactly. So it is. And that means it would be what type of discontinuity? Removable. Okay, but we're not there yet. It's fine. So just to show you, right, rewind a couple seconds. So, negative 3 squared is 9. 9 minus 0 is 9. Negative 3 plus 3 is 0. So I have 0 over 0. This is called indeterminate form. Indeterminate form, because it's hard to determine what the hell is going on, right? Normally, if we just have a number over x, oh, easy. It's a, undefined vertical asymptote. But this is indeterminate form. So we're going to deal with this later. At least this, I know for sure in the second semester. Indeterminate form, because you can't determine what is going on. Indeterminate form. This is just a FYI. So I do know my function value is not going to be defined, but it's unclear whether this is a vertical asymptote or removable or what's going on. Well, this is the first part, the y value. This first one's finding the y value, the function value. The function value doesn't exist. So I say f of negative 3 is going to be undefined. It's not defined because I got an indeterminate form. Okay, now if I find the limit, so I go back to my calculator and I'm going to graph this. So I have x squared minus 9 divided by x plus 3. Weird. It's just a straight line. Like I don't see a hole. I don't see I don't see infinite discontinuity. I don't see a jump. But if I would zoom in, it looks like it's just a straight line. So am I gonna be, if I cover up the y value at x equals negative 3, does it seem like I'll have a limit? Right? If I come over here at x equals negative 3, so let's see, 1, 2, 3. So right here, right? I'm covering it up. Can you guess what the limit would be? Yeah, you can definitely predict what it would be. This is a SAT skill, extrapolating data. Can you infer what it should be if you don't actually have the value? So remember, the limit is your prediction of what y would be. It's not the actual y value. It's what you think it should be based on context clues around it. So looking here, it seems like we're approaching the same number from both sides. What number are we approaching? So we're approaching, okay, that was not specific. As we approach x equals negative 3, what is the y value we're approaching? Negative 6. So if you look on your calculator and you draw a little line, you're like, okay, it seems like we're approaching negative 6. 1, 2, 3, go down. It looks like we're right where negative 6 is. Can you see my little guy? 1, 2, 3. I come down and it seems like we're about at negative 6. Can you see my pointer? Yeah. Okay. Seems like we're at negative 6 because I have 1, 2, 3 down. Okay, so it looks like we're at negative 6. So, second part of continuity test. Find what the limit would be. So we're approaching the same number from both sides. So limit exists. And just so we remember what it looks like. Come on. No. it looks something like, let's see, -3, -6. So it's just this little hole and it's a straight line. So the third part is saying, are these the same thing? Well, clearly, if we have a limit and no actual y value, it's not going to be continuous. But what type of discontinuity is it? Removable. So we're going to prove it to you. So this is not continuous. Because I know there's no function value. Like I know it's an open circle because the function's undefined at x equals -3. That was from part 1. We looked at the, what?
If it wasn't undefined, then it wouldn't.
If it wasn't undefined, if we had a number, then we would see it on here. So it's not continuous. It's going to be a removable discontinuity. And I'm going to show it to you. So this is what Shane was talking about. So if I fully factor out my f of x, I get, let's see, x minus 3 and x plus 3 on top over x plus 3. This is the same function, right? The same function that we started with. Let me just make this full size. Come on. Okay. So notice I have a factor on top and bottom that match. And as long as I am multiplying, right, everything on top is being multiplied, I can cross out. The reason I'm specifying this is sometimes we cross out things in binomials. Like, no, everything has to be in factored form for you to cross out things in top and bottom. So I'm going to cross out the x plus 3, and literally my function's going to be the equation x minus 3 as long as x is not equal to -3. Because what happens at -3? It's a hole. It's undefined. Okay, so literally graph x minus 3, but at x equals -3, just put a little hole. That's what this function is. That's what I mean by removal, is you literally remove the factor and it will just be a hole. You're just removing that one y spot, just right there. That's it.
Is that what we figured in the beginning? In other cases?
So there's a certain order the way I want you to approach, like, so okay, we've been going at things like bit by bit. So we went over like intercepts. Now we're talking about discontinuities. And now we're going to talk about end behavior. And then putting it all together is like, okay, I give you this function. I want to know, what are the horizontal asymptotes, vertical asymptotes, y-intercepts, x-intercepts, domain, the range, like, I'm going to put everything together, but first we got to make sure we have all the little tools in place. So I don't think that answered your question. But like, it's coming. I will be answering it soon. All right, end behavior. The end behavior function describes how the function behaves at either end of the graph, literally as x is going towards infinity. So we're taking the limit as x goes to infinity. What I'm wanting to know is predict the y value as x gets really, really big. What's happening to our graph? Predict the y value as x gets really, really small. What's happening to our graph? That's what it means as x approaches infinity and negative infinity. So right end behavior, the right end, so you're looking at the graph, right, left, right, the right end is positive, so the right end is you're going towards positive infinity. So right is the positive direction. What happens to, so literally, if I'm saying limit of f of x as x approaches infinity, I'm asking, what happens to y values as x gets really, really big, increases without bounds, gets really, really big, approaches infinity? I mean, you never can actually approach infinity, but literally, as x goes to 50 billion, million, billion, trillion, right? As it gets really, really big.
Y approaches negative.
So for our example, right, it's approaching negative infinity. Now, what is the left end behavior? What's happening to y as x gets really, really negative? So not just negative 50, negative 50,000, billion, million, zillion, right? So really, really big numbers as it goes away left end of our graph. What's happening? AKA going in negative direction. So our example up above, we are going to positive infinity because it's increasing without bounds. It's like going up and up and up. So for this example, so if I say the limit as x goes to infinity of f of x, I would say negative infinity, comma, dne. So you would need, like, you should write both. Because although the y value is approaching negative infinity, it's going, technically the limit doesn't exist. Because remember, if we're approaching infinity, you can't actually, like, say, aha, this is where 5 is on a number line. You can't actually put infinity on a number line. That's why we don't have square brackets around infinity. Technically, if you take a limit, you're trying to, like, oh, what y value are we approaching? Oh, we're not actually going to be approaching a number ever, because it's going to keep increasing forever. There's not actually a number it's going to stop at. That's why we tack on a dne. It does not exist. Yes.
Why is the graph like this? If it was turned around, would the answer change?
Turned around.
Like if the part that was going up on negative.
So if it was like this instead?
Yeah.
Yeah, then it'd be approaching positive infinity.
Okay, so it just depends on the graph.
Yep. Depends on the graph. So this is just one example. It depends on the graph. What if I had a graph like this? It was like y equals 4. What, as x approaches infinity, what's y approaching? 4, because it's just a flat line. Okay. So here we're just talking about the end behaviors. We don't care about what's happening in the middle, right? Look, oh, we're approaching 0, whatever, who cares? End. Only the ends of your graph. So, use the graph of each function to describe its end behavior. So, I'm looking at, let's see, so let's do the right first. So the right hand, the limit as x goes to, if we're going to the right, are we going positive or negative? Positive. As we approach positive infinity of my function, what number am I approaching? 0. Right? I'm getting closer and closer to 0. Right here. We don't care. We don't care about this middle stuff. Who cares? Whatever. All we care about is the ends. End behavior as we're approaching a positive and negative infinity. So I cross out this middle part. Who cares? We don't need the middle portion. Only want the end behavior. Okay, and then if I do my left, the limit as x goes to, if I'm going to the left, it's going negative. So as it approaches negative infinity, what's happening to my y? It also goes to 0. So notice I'm getting closer and closer to the 0 axis. Imagine if the graph went up like this. Then it would be approaching infinity. It's not going up without bounds. It's getting closer and closer to my x-axis, which is a y value of 0. So even if the graph looks something like, maybe the graph came down and oscillates around and it like goes this way, is still, we're just looking at the end. Where is the arrow going? If the arrow going horizontal, it will be a line. It will be like a certain number. If the arrow is going up, it will be going to infinity. If the arrow is going down, it will be negative infinity. Okay.
Do we need to write right and left?
No, but what I am expecting is like this. And you must, on the test, you have to write limit as x goes to infinity. Like, it has to be in this form. So no, in Algebra 2, you guys would write like, as x goes to infinity, y goes to 0. No, this is pre-cal. You must write it in this notation. Write it in this notation. Getting you ready and comfortable with limits. That's way when you take calculus, if you do, like, you won't be terrified and have no idea, because we use limits all the time. I'll literally show you my notes every single lesson this year so far. Limits. Yep. I forgot. Thank you. I am just not having a day today, you know? Just not. Okay. Appreciate it. Yep.
Why would it be limit of fx? If fx represents y and it's going like
It's the limit of the function. The function is x squared plus x squared. Like, it's this whole thing. So I'm looking at the graph. And I'm saying, what is the graph approaching? What is y approaching when x is going to infinity, negative infinity? I don't know if that answered your question. Yeah? Okay. Cool. So if I give you another graph, can we do it? Yeah? Okay, cool. Love the interaction. Let's try B. I'm going to give you like 30 seconds. Try it yourself. Try it yourself. Yep.
Which one is it?
So we're looking at the end behavior. So we don't care about the stuff in the middle. We only want the end behavior. And if it helps you, you can like follow this along and literally draw the arrows. Remember, end behavior has nothing to do with what's in the middle. Only looking at the ends. Where are the arrows pointing? Are the arrows going up to infinity, down to negative infinity, or horizontal to a certain number? Yeah. So you do infinity or negative infinity, comma, d. Yeah. I'm trying to get you guys in the habit of saying that. So, because technically the limit won't exist, although we're like approaching infinity. It's not the same as approaching 1. Because 1, you can like go up to the graph and be like, haha, look, it's going to 1. But infinity, like, it just keeps going. Comma, d. You don't have to write the plus in front of positive infinity, but you need to have the negative in front of negative infinity. That would probably be better if you didn't write it. I don't know, maybe. You do you. I just don't want to be confused when I'm grading. Yeah. Okay, so from the right side, limit as x goes to infinity of f of x, we're going to positive infinity. And then as we go to the left side, as x gets really, really negative, we're also, the y also gets really negative.
Why would it be negative?
Yeah, I forgot to write the DNAs. Okay. Thank you. I literally told you guys to write it, and then I did not. Yeah, did I not write it? No, the ones before is 0. Yeah, sorry, the one up here that I was talking about. If it ever circles, this one. Okay, use your graphing calculator to graph each function. Identify and describe any points of discontinuity, describe the end behavior, and locate any zeros. Yes? Because notice these are going flat versus this is going up and this is going down.
So even though there's no arrow on this, like you can't.
There should have been an arrow.
If there wasn't, though, do we then like say the exact numbers on it?
No, because I'm giving you functions. Okay, so first we see this is a polynomial. Is it going to be, are we going to have a discontinuity? If it's a polynomial, what's the domain of a polynomial? All real numbers, aka every x is defined. So we have no discontinuities. Okay. Polynomials are literally defined as being continuous. So discontinuity in type, there's none. So I gotta pull up my calculator. So I want x to the third power minus x to the second power minus 4x plus 4. So in case it's not clear, you need to bring your calculator every day to class because we're going to be having quick poll questions and we're going to use calculator skills because I will not answer calculator skill questions during a test or quiz. Cool. All right, here we go. Wow, look at this graph. So pretty. Okay, so look, it is continuous. No holes, no infinite discontinuities. What is the right end behavior? All right, so notice that there's no arrow on it, but you know, if I zoom out, it just keeps going up and up and up. So the right end behavior is going to be positive infinity, comma, dne. And what is the left end behavior? Negative infinity, comma, does not exist. So I want to be clear. Why am I saying it does not exist? So normally when I'm like having a limit, I'm like, aha, look, I'm approaching a number. I can put my finger on it. This is the limit. Got it. If there's no limit, because we have a jump, or approaching trigger numbers, we say it doesn't exist because we're approaching trigger numbers. Here, we say limit doesn't exist because as soon as I'm like, this is where infinity is, JK, it just keeps going down. You can't actually like point to it on a graph like where infinity is. So whenever you have an infinity, you always say DNE. It's the same reason why we don't use square brackets, we use parentheses for interval notation with infinity. Yeah?
So what would an example be like if there was an
Okay, let's see. Do I have an example? So far, for I'm only giving you like going towards the x-axis, which is 0 or infinity and negative infinity. When we cover horizontal asymptotes, that would be literally it'll be going toward your horizontal asymptotes. So we'll be getting towards that 1.4, I think, in this chapter sometime.
Is there a reason that there's like a lighter part on the graph?
A lighter part?
Like on a lighter part?
Oh, it's because this text is above it. Yeah. Okay, we want the zeros, so we need to actually find the zeros. We don't want to do algebra, so let's use our calculator. Menu, analyze graph, 0. You have to put it to the left of the 0, move it to the right, and I see one of them. I'm going to use a shortcut. Check it out. Look what happens if I keep dragging it. It like pops up all of my zeros. Well, it should. I don't have to go do this, and I don't have to do this more than once. So it shows that one of my zeros is negative 2, 0. I keep dragging it, and it shows another 0 is 1, 0. And then my other 0, I'm going to have to do it again. Just trying to get it so it would just show me. You know how if you click to the left of it and you keep scrolling, it'll like show you so you don't have to like, do the whole process again. Okay, once again, analyze graph, 0. To the left of it. Okay, 2, 0. So we have 3 zeros. And keep in mind, literally, a 0 of our function, there's multiple ways I can say this, multiple synonyms. I can say x-intercept, root, solution. They all mean the same thing. Root, solution, x-intercept. Wonderful. Try the next one if you haven't already. If you're done, go ahead. Yeah. So if you want to easily clear everything, including our zeros, just menu, action, delete all. That way it gets rid of everything we did. We can graph this again. How's a what? It didn't have a very good 0. So there's 2 zeros. Right? You can see the one that's like at 1.1 or something, and then it's actually crossing. It's crossing it again, like on that left graph. You see how it's above, and then it like dips below. It's kind of hard to see. So this is why we're really going to depend on our calculator for this one. Okay, so first, do we have discontinuity? Yeah. Okay, yes, we do. And where is it located? What type of discontinuity is it? It's infinite. How do you know it's infinite? Exactly. We have our graphs. One's going positive infinity, the other's going negative. That literally shows like, wait, how like it never like comes back, right? It never like turns back toward each other. It's going opposite ways.
So you can't figure that out without using the calculator.
We could. So whenever the bottom of my fraction is equal to 0, that's where an asymptote is going to occur, unless you have a removable. You have to check for removables before you say, yes, this is where my vertical asymptote is. Once again, I'm getting like a section or two ahead of myself. So it's infinite. Where is it occurring? At x equals 0, because the only time when x cubed is going to equal 0 is when x equals 0, right? You set your bottom of your fraction equal to 0. That's where you'll have undefined. And then, let's see, right-hand behavior. Am I approaching a certain number, or am I going up to infinity or down to negative infinity? Am I like leveling off to a certain number? 0, right? The right end behavior is 0. And what about the left end? Yeah, right? It's not like going off to infinity or like down to negative infinity. It's like leveling off and getting closer and closer to 0. And then I have to actually find the zeros. Okay. So I gotta go menu, analyze graph, 0. I'm gonna put a way over here because I have no idea where the 0 is. Oh, here we go. Negative 4.19 comma 0. Let's see if I can get 2 for price of 1. No, didn't show my other one. Okay, that's a nice try. You said 1.19? Wonderful. Yeah, 1.19. Cool. Okay, so that's a pretty good place. Let's have Bradley, then Andrew. This is, I wouldn't give you a question like this unless you could actually have a calculator. Because like 4.19, no. I would look at this question and give up before a calculator.
If it was like a whole number.
Yeah. So this other one, I could have had you factor the polynomial and find the zeros. For this top one, I could have had you do that, factor by grouping, etc. Did you have a question?
Was there a mistake with the last 10? So they're like 40 problems.
No, they weren't.
For 1.2, they're like 40 problems. Like I did it, but
Let me look. So 1, 3, 5, 7, 9, 11, 13, 17, 19, 21, 23, 25. Did I mean to do every other odd? 27, 29, 31, 33. There's like 20 some problems. Because it's the odds. So you're not doing the evens, you're just doing the odds.
yeah, I know.
No, it almost went in.
Yeah, but
That one is.
I don't know what you said.
it's still very lengthy.
It also, yeah, it also was like 2 days of lesson. Yeah.